Hi, let's go ahead and let's start chapter 2 where we're going to talk about our data. And right now, we're not going to do anything with calculating these things. We're just going to talk about general ideas. So let's go ahead and get started. So we're going to talk about looking at the data and seeing the distribution. That's both numerical and categorical. We're going to talk about summarizing these things, but we're not going to summarize them with numbers. That comes in chapter 3. So this is section 2.1. So what we're going to do as we do this is we're going to look at the distribution, and we look at shape, center, and spread, which can also be called variability. So here's an example of some raw data, and what we're going to do with that is raw data doesn't tell us much. So the first thing we do as statisticians is we put them in frequency tables. And so we look at the values and how many times did they show up. That's what a frequency table is. Now, do frequency tables help us a whole lot? No, they don't, because it's still difficult to see. So what we do is we try to picture the data, and we do that in different ways of examining the data. So we want to visualize it, we want a picture that tells us what's what. So graphs that do that are dot plots, histograms, and stem plots. And we'll look at how to do those in StatCrunch. So when we look at the data, we look at the shape. Is it symmetrical? Do we look at the center? Is there a most common value? And we look at the spread. How far apart are the data values? So when we look at the shape of the data, we are going to see if it's symmetric, and it could be bell-shaped, and there are other symmetrical shapes we'll look at in just a minute. Is it asymmetric? It might be right skewed and it might be left skewed. And we look at the modes, and the modes are the numbers that happen the most often. So when we're looking at graphs, we're looking at the mounds. Is there one mound, two mounds, multiple mounds? So here's a symmetric bell-shaped curve. Here's a symmetric mound-shaped curve. Here's a symmetric uniform distribution. Now the uniform distribution might be something like we ask 1,000 people what the last digit of their social security number is. It really should be uniformly distributed between the digits 0 through 9. That's a symmetric uniform distribution. Now when we look at asymmetric distributions, we look at it as where does the tail point? So think of it as a sleeping brontosaurus, and the tail points to the left, so this is left skewed. An example of a left skewed might be the grades on a very easy test. Most of the grades are going to be higher. There's going to be very few low grades. And then the next type is going to be asymmetric skewed to the right. This might be something like if we do a historical survey on the salaries of Major League Baseball players. There's a whole lot of baseball players that got paid very moderately, but as times go on and superstars get huge salaries, but there aren't very many of them, that would be skewed to the right. Here's an example of a data set, and so we have the pulse rates in beats per minute of males and females. Now this is not in your textbook, this comes from another Pearson book. But if we would take the female data and put it in a frequency table, it's going to look like this. Now, here's the deal. When we do frequency tables, we usually do binning, and that's just a fancy word for categories. Okay, so think of if you are sorting out colored paper and you have different bins, waste paper baskets, and you put the red paper in one basket, the blue paper in another, the pink paper in another, the orange paper in another, the yellow paper in another. You've got bins. So now the important thing when we do a frequency table is that our data can only fit into one category. And so you can see this one goes 60 to 69, 70 to 79. So there's no ambiguity on where that piece of data fits. If sometimes you see 60 to 70, 70 to 80, 80 to 90, and it'll say the data, if the data is 70, it goes into the lower bin. Okay, but it has to be defined. The data can only fit into one place. So when we visualize the data, we want to see patterns. And so the picture must record the data values and indicate the frequency of them. Okay, now here's another data set. And as you can see, it's kind of an elderly data set, but it's pretty good. So the professor at Virginia Commonwealth University looked at one section of her introductory statistics class in the spring term of 1997. And here's that data. Okay, so you can see this data isn't in order. It's self-reported, but we have 63 students. Okay, now let's put that data into a frequency table. And so here we go. And this is one way to look at frequency tables, 100 to less than 120. So you know if an individual scores 120, they're going to be in that second group. And you can see the numbers. Now, the stuff on the bottom, the information on the bottom is not extremely important. What that does, it gives you just a guideline on how to set up your frequency tables. And this will not be on any test that you do, but you take the number you have in your data set, do the square root, round it up to the nearest whole number. So we want to have 8 intervals. We look at the range from 260 to 100, which is 160 divided by 8, and we get 20. So that's how they came upon the class width of 20 pounds. It works kind of nice, all right? So this is your data on page 39. It's the distribution of the number of goals scored by first-year women's soccer players in the NCAA Division III in 2012. Okay, now how do we make a dot plot? Okay, here I have the data from the goals for the NCAA Division III in 2012. I don't have the frequency table. This is the raw data. But I'm going to go graph, dot plot, and I'm just going to do, I've got to select my variable and compute. And there it is. And this should look like the one in the textbook. Let's look at how we do a frequency table. I'm going to do tables, frequency, variable 1, compute. And then I get a frequency table very much like the one that's in the textbook, as well as the relative frequency given to me in decimals. So I just want you to know that that's how that works. So they made a dot plot using these values, and how many times they happened, there's that many dots. Now, in a different example, what's the cost of the textbooks? We can look at this, and here is the value of our textbooks. We can look at how many textbooks cost $150 or more. 1, 2, 3. What percent of the textbooks? Well, we'd have to count up all the dots, and then we're going to do $50 or less. Count up these dots, 1, 2, 3, 4, 5, 6, 7, 8, divided by how many we have, times 100. Are there any unusually expensive or inexpensive text? Well, this one text that's almost $300 is kind of unusual. Art textbooks are very expensive because of the printing. So 4 textbooks cost $150 or more. 8 out of 23, or about 34.8% of the textbooks cost $50 or less, and that $300 textbook isn't usually expensive. So, dot plots. They show individual data values and help us look at the distribution. They're not as common as histograms and other graphs, and they're not great for data with too many individual values. When you are in a program and it does dot plots and you have a lot of data, they might say each dot represents 7 individuals. So now let's go on and let's talk about a histogram. And we've already looked at a histogram. And we put the data into intervals and we call them bins. And when we do that, it's called binning. And we want to know, we can pick how many data values fall into each bin. So each of the rectangles in our histogram touches the other one, showing that we have continuous data. Oh man, didn't want to do that. And the first value in each bin can be recorded on the horizontal axis. Sometimes it is the midpoint that is recorded on the axis. And the height of the rectangle corresponds to the count. So here is that data on number of goals, and you can see that we have our values from our frequency table, and then the frequency is on our vertical axis. Now 9 to 12, so you see we went 9 to 12, so that means we're going to have, but not 12. So that'll be these 5 are in our first rectangle, and then from 12 to 15 will be these 9, and then from 15 to 18 will be these 6. 18 to 21 will be these 6. Now I have a bone to pick with this, in that, oh, they are. I was going to say our bins aren't even, but they are. They're 3. They go up by 3 each time. So that's good. And you can see that we have this one piece of data that's far out from the rest of them. Might be an outlier. So we can change the bin widths, and this would be bins of 1. So it changes what our histogram looks like. Now, this is the data, the weight data that I showed you earlier, and this is where we have the note. The left endpoint is included and the right endpoint is not. So you can see in that class of statistics students, we had 7 who weighed between 100 or more, but less than 120. We have 12 that weighed between 120 and less than 140, etc. And so you can see we have one individual who weighs somewhere between 260 and less than 280. Now, when you do your histograms, if your bin width is too narrow, you get too much detail. If it's too wide, it hides the detail. Most technology chooses the bin widths for you, but you can always adjust them later. So what are histograms good for? They're good for a large data set. They help us focus on that general shape. Disadvantages: individual data values are not visible, and we can affect the shape, kind of, by choosing different bin widths. Now we have stem and leaf plots, and stem and leaf plots give us that individual data. These are very easy to do by hand, especially if you have a piece of graph paper. So when technology isn't available, or when the data set is a moderate size, stem and leaf plots are pretty easy to make on your own. The first thing you want to do is you want to put the data in order, okay? And we're going to draw on this. A lot of times you will draw a line. The stem here is on the left and the leaves are on the right, and notice I had 5 ones occur, so I'm going to write 1 5 times. I have 3 2s, so there are 3 2s there. All my 3s, my 1 4, all my 5s, all my 6s, all my 8s. Now the stem here stands for 10, so I put the 1 there, and 1 10, 2 10s, 15, 17. Then for 20, I have 20 exactly and 25. 30, I have 2 30s, so I just put the zeros there. And 40, so I can see that this is going to be a skewed data set. If I could turn this to the left, it would look a lot like a histogram. Now, here's the stem plot for our weight data. So it's always for quantitative variables, and we separate the observations into the stem and the leaf, okay? We write the stems in a vertical column and then draw a line. And then we write each leaf to the row to the right. So here's our weight data, and it isn't in order here, but we are going to put the first 2 digits as our stem and the last digit as our leaf. So let's write our stems. So this would stand for the 100s, 110s, 120s, 130s, 140s. And so when we put a 3 here, that would stand for an individual who weighed 203 pounds. Okay? So if our individual is 192, we're going to find the 19 line and put the 2 behind it. 152, we're going to put that 2 in the 15 line. 135, we're going to put that 5 in the 13 line. And I think you can see when we put it all together, there you have the data in order. And if we would turn this again to the left, it would look like a histogram. And you can see, just roughly, it's not very regular. But you can also see that it's kind of skewed to the right. If you have data with very few stems, sometimes we split the stems. So if all of our data were between 150 and 179, we could split the stems. And then what you do is you put the first 5, 0 through 4, on the upper stem, and then the last 5, 5 through 9, would go on the lower stem. And it gives you, I'm going to go back to that, it gives you a little bit more information. Okay, now let's keep going and let's talk a little bit more about shape, center, and spread. So, is it symmetric or skewed? How many mounds appear? Are there unusually large or unusually small values? That's shape. So again, we talked about the symmetric bell-shaped curve, and it's roughly symmetrical. When it's skewed, remember our dinosaur, it trails off. This one trails off to the right. This one trails off to the left. So the blue one is right skewed, the tan one is left skewed. So when we talk about the mounds, the mode is the name of a piece of data that happens the most often, and that's where your histogram would be the tallest. When you have one tall, it would be unimodal, one mode. When you have two bumps, it's bimodal, in that you have two bumps. When you have more than two mounds, then it's multimodal. And the mounds don't have to be the same height. Sometimes if you look at the data and who the data was captured from, you might want to split it up. For instance, you've got men's and women's heights. Then it makes sense to split it up into two different groups. Or you look at afternoon and evening sales at a restaurant, especially when they have lunch specials, which are smaller portions at less cost. They're two distinct populations, so it'd be better to look at the data in two different graphs. Okay. What would you expect to see in a histogram of the following data sets? GPA of college students are probably going to be pretty bell-shaped. SAT scores are probably going to be skewed to the right, where most people are average, but there's a few extremely high scores. Last digit of social security numbers, that's going to be a uniform distribution. The income of residents of the United States is probably going to be, most people make a moderate amount, but there's a few people that make oodles. Okay, so they say that GPA of college students are going to be skewed to the left. Okay, so let's think about what that's going to look like. A few very low GPAs. SAT scores symmetrical. Last digits symmetrical and uniform, and income skewed to the right. Now, when we look at outliers, they are things that are removed from the pattern. Okay? Now, there are definitions for outliers, but we need to work with numbers before we do that. And usually, if someone is designing a study, they will define those outliers. So what happens when you have extremely large or extremely small values? Well, you need to report those values. They could be a typo. They also could be actual outliers, meaning they're pretty interesting. They also might be, let's say you are measuring the weights of newly hatched ducks, and you get one outlier. And I'm thinking of the story The Ugly Duckling, where a baby swan, who's called a cygnet, got in with the ducks. Well, they're bigger and they look different. And that would be someone who didn't belong in the population. So center. So again, center is our typical value. In chapter 3, we're going to talk about numerical values of typical. But you can see here's typical is going to be 16 goals. Okay? So it's kind of in the middle. For men, it's going to be 13 goals. So the typical male soccer player scores fewer goals in a season than the women. But if we look at the horizontal spread of the histogram, if all the data values are similar, we have a very narrow graph. If the data values are different, we have a very wide graph. And to me, this one goes here and that one goes there. So when we have numerical distributions, we want to look at the shape, the center, and the spread. So let's talk about categorical variables for a minute. How do we do categorical variables? Well, when we want to do a treatment similar to a histogram, we use a bar chart. And the thing that's different about a bar chart is the bars usually don't touch because the data is not continuous. We can put those data values in any order that we want. So here we go. We've got first year students, sophomores, juniors, seniors, and graduate students. And we're going to look at those. So there's really no rhyme nor reason for how we did this, except I'm not sure why we left off first year students here. Oh, because there aren't any. So we don't have to put anything there. So you can see, and relative frequency is the percent, that a small part of our class, our introductory statistics class, is graduate. We don't know about 35% of the class, but of those we know about, seniors are the biggest group. Now, in a histogram, the bars do touch, and I'm going to get that out of there. If they don't touch, that just means that there is no one in the class next to it. They do not touch in a bar chart. The bar width corresponds to our bin width. Now, our bar width can be any width we want, but they all need to be the same. And our horizontal labels in a histogram are numerical. In a bar chart, we can put them in any order we want to. Now, a Pareto chart is a special kind of bar graph where the bars are arranged from tallest to shortest. You can't rearrange the bars in a histogram. Greatest to least, then you get a Pareto chart, and this is some data of how did you learn about the job. And notice they're all together, and I have a problem with this in that the bars touch. They really shouldn't. In a pie chart rather than a bar chart is you don't know the values. It's just easy to see the proportion of the group. And again, let's look at how we summarize categorical distributions. So again, we're going to do shape, center, and spread. When we do categorical data, we look at the mode, or the most frequent outcome, and the spread, the variability. When we look at the mode for categorical data, they're going to be roughly the same height. They happen at the same rate. Again, unimodal means 1, bimodal means 2, multimodal means more than 2. So here we have a new group of 2,508 Americans, which economic class they identify with. So they don't know lower, middle, upper. So the mode is here in the middle class. So when we have high variation, each value is represented at about the same frequency. Low variation, a few values appear many times. So variability here is how many values you have rather than frequencies. So here we have ethnic composition of 2 schools in the LA City school system. So you can see that there's more variability in school A in that they have more of their students in all these categories. Where school B, it looks like we have students in only 2 categories. So let's talk about interpreting graphs. So with numerical data, we're going to do dot plots, histograms, stem plots. Categorical data, we're going to do pie charts and bar graphs. And we always want to talk about shape, center, and spread. So shape, when we're talking about categorical data, is how many modes. We really can't talk about center in categorical data, and our spread is variability. How many different categories do you have? So you need to watch for inappropriate scaling, using icons of different sizes rather than bars. Watch for data that starts other than 0. In your book, you can see this on page 58, but here's another example. Here is just, do you agree with the court decision to have the feeding tube removed? And they looked at this data. This data would be from when the parents or the significant other have to go to court to have the feeding tube removed from a patient in a vegetative state. You can see that this looks like there's a big difference depending on party. But notice that here we start at 53%. This looks like a huge jump. But when we start at 0, it doesn't appear to be such a big result. So watch for that. That is how many graphs are misleading. They have a non-zero axis. In the book by Tuft, the visual data set, when you have less than 20 individuals in your data set, use a table. Even though they're pretty, you don't want to use that kind of graph. Examples of the worst graphs ever are found on the front page below the fold of USA Today. They put all kinds of graphs in there, and most of the time they're pretty bad graphs. So we don't want our graph to distort the data, and the ink should be in the graph and not the design features. So make your graph meaningful, not pretty. Don't use cross-hatching, slanted lines or dots for shading, and don't use areas or volumes for one-dimensional data. Here's an example of that. Here we look at a $1980 and the value in 2005, and you can see, oh my gosh, it is tiny. But notice that we are looking at two dimensions. We are looking at area. Now, in all reality, the $2005 is 42% of the $1980. When we look at this tiny one down here, and I'm going to try to draw it up here, it is definitely not 42%, which is almost a half. You can see that it's about maybe a sixth or an eighth of that dollar when we look at that area, and our brains register the area. Statistical graphics describe the data. We look at shape, center, and spread. They reveal characteristics of the data set, and we can compare data side by side. And whenever you start a study and you get your data, the first thing you always do is you graph your data. Notice that graphs that are not good may contain errors, and while they can be technically correct, they can be misleading. So our goal here is for you to become a savvy consumer of graphical statistics. Pictographs can also be misleading, and again, it's because we are comparing areas versus this is just linear data, so we should not have, it's one-dimensional data, we should not have two-dimensional pictures. And here we have the same data using three-dimensional blocks. That's even worse. Here is a good representation of that same data. All of our rectangles are the same width, and so we can compare their height, and it is a much better comparison.